So today my talk is about the FPGA training implementation of a time series forecasting network using the block Minifloat arithmetic. So I like to bring my talk into the five parts, and the first one is the introduction of this work. So the training on edge enables the model to have more flexibilities so that the neural network on the edge can adapt to the changing conditions. And one of the important applications is the time series predictions, such as Internet of Things, IoT, or the sensor data forecastings. However, the problem for training implementation is the training itself is approximately 3 times more memory and computation resources requirement for 1 minute batch trainings compared to the inference. So it has forward pass as well as the back propagations. In back propagation, it has the error propagation as well as gradient computations. And one of the minor part is weight update. So one of the solution is to use a custom number systems to reduce the memory and computing resources. So there have been several publications about the low precision implementations. So we can see there's many like 4-bit or 8-bit quantization methods for training applications. Some are for the general neural network, some are for the large language models. But however, these quantization methods are not hardware friendly. And also on hardware implementations, for on the FPGA or ASIC platforms, there we can see many 8-bit implementations which use a logarithmic number system LNS or FP8 8-bit floating point or block floating point. And also Microsoft with other vendors proposed the micro scaling arithmetic actually is quite similar to the block Minifloat we will talk today. So the aim of this work is to explore the feasibility of applying block arithmetic to trainings. Firstly, we need to explore the low precision block BM arithmetic for trainings and develop an efficient BM GM architectures. These 2 points could be applied to other applications. And based on the BMGM as well as arithmetic implementations, we develop a training accelerator for the time series predictions. So more specifically, we implement the N-bits neural network trainings. So firstly, let me talk about some concepts. For the block Minifloat number systems, we could simply regard it as a combination of Minifloat and the shared exponent bias. So here is one example of the block Minifloat format. So the dashed line here, inside it represents a block. So inside one block, it has several elements, and each element is represented in the Minifloat format. And one block has a one shared exponent bias for the whole block. And usually we'll write the data format as BM EM. So here, E and M represent the word length of the Minifloat exponent and Mantissa word length. And also, the block Minifloat could be regarded as a kind of generalization of the block floating point and Minifloat and other kind of arithmetic. Also, in the block Minifloat matrix multiplications, we also need to introduce the concept of the block size and the mixed precision in the BMGM computations. So here is one example of the matrix multiplications. So sometimes we will set the block size equal to the matrix size or the tensor size for the hardware implementation convenience. So in that case, one tensor or one block will share, one tensor or one matrix will share a common shared exponent bias. And however, in many AI algorithm-based training papers, we usually partition the matrix or tensor into a lot of small blocks so that to increase its training accuracies. So And also, I need to mention that the tile size is not equal, not the block size. The tile size is a term that relates to the hardwares. So usually we prefer to maximize the tile size to fully utilize the on-chip resources, while the block size will be as small as possible to improve the training accuracies. And we assume that the tile size is equal or bigger than the block size. So during the matrix multiplication, we need to cross different blocks in the inner product, and also bring the difference in the arithmetic implementations. Another one is a mixed precision gem for the different training phase. So in different training phase, in the forward and backward, we will use different input variables like activation, weight, gradient, error. So for these variables, we will have the same word length. However, they will have different exponent and mantissa configurations. And this mixed precision can also used to improve the model training accuracy. So in this work, we proposed an implementation of block Minifloat for the MB's trainings. We propose a novel technique for cross-block BM matrix multiplications, as well as mixed precision BM gems. And based on these, we propose the implementation of 4-bit BM training on MB's neural network with DSP packings. And the results show that the training result can get the similar accuracy to the floating point 32. And for the hardware performance, its power efficiency is 3.75 times higher than Tesla M40 GPU on Aveo U50 platform. And then I will introduce about the MB's neural network and its training implementation. So in the figure here, illustrates MB's neural network, and in the middle is network. So inside this network, it involves several MB's blocks, and MB's blocks is illustrated on the left. And beside MB's block, it also have a lot of like residual interconnections, and the residual interconnection is represented with a high precision with a longer word length, and use a yellow color. And on the right is MB's block of the error propagations. So in each FC layers, after calculates each layer error result, then we will calculate its gradient and then do the weight update. After that, then we do the next layer error and follow the chain rule. So the major computing part of the MB's training is a FC layer forward and backward computation on the gem block. So the gem block is determining the performance of the MB's training performance. And for the MB's neural network, it uses SMAP loss for trainings. And during validation, we use SMAP loss for validation on M4 dataset. And the formula is written on the right. And for these two laws, so it is smaller, the better. So here is MB's training accelerator implementations. On the left is the diagram of the systems. So before trainings, the CPU will load the weight and data set from the DDR memory onto the Aveo U50 board and to the HBM memories. So inside the HBM memories, it will have the weight of the whole models and the data set, as well as the activation that generated in the forward pass. And that activation will also used in the gradient computation during the backward. For the programmable logic, we have like low precision buffer and high precision buffers. And the low precision and high precision difference is the word length. And for the computation block, we have a FC block and several different vector addition block, SGD, MAP loss, and other things. They are all implemented in the BM format. So the FC block accelerates the FC and linear layer in trainings. It's the major block. And inside the FC block, the BM gem is a dominant part. It's an outer product P arrays. And feeder A and feeder B will pre-process the input data for different training phase. And here we mark the 1, 2, 3 label on the feeder A, which represents the forward, error, and weight. We will do the transpose and do the derivation of ReLU and some other kind of computations. Okay, so this is the training implementations. And now I will introduce about the BM arithmetic implementation and the BM gem. So here we provide an example of the implementation of the BM matrix multiplications. So in short, we could consider the process as we get the Minifloat input data and then convert it into the integer and then do all the computation in integer and then convert back to the Minifloat format. So here in these examples, we have made two input matrix A and matrix B, and A element A0 to A3 and B0 to B3 are Minifloat element. And it belongs to two different blocks. So in this, when do the inner product in the same block here, for example, like A0 and A1, we will convert it into integer and then do the FMA operations and store it in the rest registers. And after one block in the product finishes, then we accumulate the rest register result into the P-sum register and do the interblock accumulations. And because the rest register and P-sum register will have different share exponent bias, so aligned addition is needed. And after the inner product, we can get a block of the accumulation result, P block square arrays. So the accumulation result is stored in the integer format, and then we will convert the integer accumulation result P into the BM format output. So in the normalization, we will have two steps. First is to find the maximum in the block to avoid overflow when do the norm part. And then if there's no overflow, we can directly convert it back. If there is overflow, we need to do the right shift of the whole block result. And the norm block responsible for the integer to Minifloat format conversions. And here, oh, sorry. And here, the integer-based implementation also makes the mixed precision implementation easier. So the computation process is unchanged, and we only need to do is in the input part, we add a mixed precision decoder for it. And for the output in the norm block, we use a selectable boundary threshold for different configurable precision output. And based on the arithmetic implementations, we propose our PE design like this. It's responsible for the scalar inner product computations. The PE has two inputs, A and B, with Minifloat format. And delta is a bias of the share exponent, which will be used in the interblock accumulations. So inside the P, it has a mixed precision decoding and FMA and interblock accumulations. When the computation finishes, the P-sum result will return to the shifter register, and it will be pipelined out to do the normalization part. And this is the BM-GM architecture. It is shown on the left. So the BM architecture also have two parts, the inner product and the normalizations. So here in the P arrays, So the block size is configurable. And in these pictures, we provide an example that with 4 blocks, which is divided by the red dash line here. So inside each block, we will have a Shakespeare block computation, a computation block beta. It will calculate the Shakespeare result as well as the bias that will be used for each piece. And on the right is its implementations. So we can see that it's a native implementation of the GEMS. It has 4 steps from inner product, find maximum, and norm. And however, it will have a long latency that brought by the normalization part. So to shorten the latency, we apply the pipeline implementations. So for the normalization and inner product between different tiles, there's no data dependencies. And also inside the normalization step, which is step 2 to step 4, there's no data dependency between different blocks. So in that case, the pipeline implementation latency will be similar to the fixed point exception overhead. And also, we propose the DSP-packed PE design that is optimized for the 4-bit BM trainings. So on the left is the DSP-packed PE design. So each PE has 2x3 import, 2 importing A and 3 importing B, and it has 6 MAC unit. And one PE has one DSP48 block. And on the right is MAC unit designs. So on the DSPs, we pack the significant modification. Here the significant modification is marked with red, and one single DSP will pack 6 significant modifications. And also, since in the 4-bit implementation, the bit word length will be small, we've merged the FMA step into the integer block accumulation as line additions. And for the other part of the logic, we will implement in the lookup table. Okay, so this is the architecture design of the training accelerator and BM gem block. Here is some of its results. The results is divided into 2 parts, the gem part as well as the training accelerators. So the first one is a block size configuration explorations. Here we have a gem block with 32 by 32 PEs, and we try the different block size on that ones. It shows that the block size has small impact on the gem areas. And also when the block is becomes smaller, there's only a small increase in the block size. And then we explore the EM configuration as well as the mixed precision configuration. For the EM configuration, we try the BM4 as well as some BM8 configurations with a uniform import and uniform output precision. For BM421 and BM825 and BM834, it has a similar area. However, the BM43 and BM52 will have much larger areas than the precision above, which it grows exponentially. That may also relate to the implementation because we use integer-based implementations. And on the right is the mixed precision configurations. We use the uniform BM25 and uniform BM52 as the baselines. So we change the output precision as well as the input precisions. So we can see that the gem with the input 25 and output 52 will have similar area as the BM25. That means the output precision configuration is has less impact on the areas. However, the configurable BM25 and the BM52 will have larger areas than the uniform 52 configurations. So the largest input Minifloat exponent word length determines the area. And for the training accuracies, we get the mixed 4 mixed BM4 precision of 14.45 and close to the FP32 result. Here is the three factors to increase the accuracies. So firstly, we can see that for the BM8, it gets almost the same accuracy as FP32. And for uniform BM4, here the uniform BM4 means for all the variables as also for the residual interconnections we represented in the BM03 format. It gets SMAP loss as 32.01. So when we use a high precision residual to the 16-bit, it will decrease from the 32 to 23.21. And then further, we use the mixed precisions on it. It will further decrease to the 15.69. And then we use a smaller block size, downgrade to the 16 by 16. The SMAP loss will go to 14.47. That is the close number to the floating point 32. And then we verify the accelerator on the hardware. The target FPGA we use is Arvil U50s, and we propose two implementation versions. The first one is the non-packed versions on BM8 and mixed precision BM4. The gem size is 32 by 32 Mac unit. The batch size is 1024, block size 16 by 16, and SMAP loss is 14.47. And for the packed versions, since we have a larger gem with 72 by 72 Mac unit, so we have adjust batch size as well as block size for the hardware configurations. The batch size is 1080 and block size is 12 by 12. SMAP loss is still as a close values 14.9, 14.5. And the baseline GPU we use is Tesla M40, which is available in our lab. And it uses the same setting as non-packed versions. And we use NVIDIA SMI tools for the testing. So here is the result of the training accelerators. So in the non-packed versions, the mixed BM4 has 31.1 less VRAM and 20% less lockup table than the BM8. And for the mixed precision BM4 packed versions, the accelerator gets a throughput of 779 GOPS, DSP utilization of 0.7 GOPS per DSP, which is state of art, and power efficiency is 42.4 GOPS per watt, and it's about 3.7 times better than the Tesla M40. So in conclusions, so in this work, we propose the M-based neural network training implementation with the block Minifloat. So in accuracies, we use a smaller block size, mixed precision, and high precision residual to improve its accuracy in the M-based neural network. And in the BM arithmetic, we propose the BM arithmetic implementation, BM gem, and 4-bit DSP packed PE. And based on that, we implement the M-based training accelerators, and the result shows that it has a better power efficiency and the good DSP utilization result. Okay, so this is my today's talk, and thanks for listening.